All right, so how we doing physical science? I haven't done one of these in about a year, but I do think it's important that at least once a unit, if not twice, I do one of these video lectures to kind of get you the skills you need to um, make that next step as a sophomore or as a junior. So these will appear occasionally. I'm not by all means going to say I'm the best video recorder of all time, or that this is going to be the highest quality video, but we'll do what we can to keep you entertained and get you some information about chemical reactions, because that is where we are headed in our chemistry unit. So in the last unit, which in the last unit, we talked a lot about atoms and the periodic table and solids, liquid, and gases. In this unit, about chemistry, we're going to take those and apply it and kind of talk about how all of those different things come together and kind of like make and build what we know today in our universe. Because without chemical reactions, we can't build anything. You can kind of think of it as our Lego blocks. Without them, there is no universe. So a couple things we need to understand is everything is made of chemicals. And when chemicals change or combine with other chemicals, we get a chemical reaction. So any compound that we have, whether that's NaCl or table salt, whether that is sugar, whether that's any of the digestive properties in our body, everything is created through a chemical reaction in one way, shape, or form. And that's how we build stuff up. So simply, when chemicals change or combine with other chemicals, we get a chemical reaction. Now, some review I want you to think about. So right now, after I read through these 6 questions, I want you to pause the video, and you should have a notes page. If you do not, you should go ask me, Mr. Wells, for a copy of that. I would like you to do it paper, pencil, unless you have approval from me to do it in a doc. You can pause at this point, and I want you to try to answer these questions. Once you answer those 6, you can unpause and continue this video. All right, so you just paused this video. Let's go through and review these 6 things. So what exactly is a chemical change? Because that's what chemical reactions are all about, is causing chemical change. So a chemical change is simply when a chemical or a substance is forever changed into something new. So in the last unit, we talked about how a chemical change is when you burn something or when you cause something to rust, where it has permanently been altered and you have something completely new and can never go back. If you have a campfire and you're throwing wood and oil and all these other things onto it, once you put that flame on it, it is beginning to go through a chemical change, and we can never revert it back to those logs, and we can never turn it back into that oil. What is an ionic bond? So this came from this unit specifically. An ionic bond is anytime you have a metal and a non-metal, and they are stealing or giving electrons to each other. That creates a positive charge and a negative charge that results in bonding. Because just like with magnets, if you have a positive, it wants to be next to a negative. If you try to put a negative and a negative next to each other and a positive next to each other, they repel each other. What is a covalent bond? So a covalent bond is the other major type of bond that we've discussed at this point. A covalent bond is when the electrons are not being stolen or given. They're actually being shared, and the electrons move and orbit around both atoms, not necessarily equally, but a little around both of them. And we'll get into that more specifically later on in this unit about how ionic bonds and covalent bonds are actually going through this process. What is a compound? A compound, remember, is any material where you have 2 or more elements chemically combined. You cannot separate a compound by a physical mean. It has to be separated via chemical reaction, which is why we're talking about it in this particular slideshow about chemical reactions. And what is an element? An element is the most basic building block of atoms. You can't simplify it anymore. If you have a bar of gold, that is an element that is made entirely of Au atoms or gold atoms. If you have an iron bar, it is completely made of iron. It is an element. All right. So these are some important things that we need to understand before we can start going into these chemical reactions starting at this moment. Give me a second while it clicks forward. Oh, I got to do it on my computer, don't I? Yep. All right. So chemical reaction. Process by which atoms of one or more compounds are rearranged to form different compounds, or simply a chemical change. So when you have a compound, so let's say you have H2O or water, and you chemically combine it with another compound, let's just say HCl. When you combine those two through chemical reaction, you produce something completely new. So like if you combine those, you might produce H2 or hydrogen gas, which is a common gas around us in the air right now. Or you could produce O2, oxygen gas, which is what we breathe and require to live. But some examples of things that commonly affect you every single day are digestion. When you put food into your body, it is being chemically broken down in your stomach through HCl, hydrochloric acid. And that has permanently changed the atoms, the nutrients in that food goes into your body. And anything that isn't being used is then expelled out of your body. And I'm not going to go into too much of the details about that. Number two, vehicles to run. So our current vehicles run on internal combustion engines. An internal combustion engine relies on fire and burning, and that itself is a chemical reaction. We put gasoline under pressure, we put a spark to it, and it explodes, which allows our engines to run. Our muscles, kind of going off of that running thing, are chemical reactions. Without the use of sodium and chloride in our body, we're not going to be able to move our muscles. And then the last one that I actually have written down is combustion of wood, which we've talked about quite a bit at this point. You burn wood, it is chemically changed. Anytime you're dealing with fire, that's a chemical change. Now, what are some other counter reactions that affect you every day? I would like you to pause the video at this point, and on your note sheet or using the internet, I want you, or your textbook, any of those work, I want you to quickly just come up with some things and write down on your note sheet what are some chemical reactions that affect you beyond the things I've talked about. So go ahead and pause the video and do some quick research for me. Take like 3 minutes to do so. All right, you just did 3 minutes of chemical reaction research. What are some things that you came up with? Hopefully you wrote those down. What are some ways that we can tell a chemical reaction has occurred? So we have a acronym or a word that we can use to kind of talk about what are some things that we can tell if a chemical reaction has happened. So I'm going to go and write those down on the board for you. So here we have facts, F-A-C-T-S. If we write this down here, and I'll write in red, F, fizzing. So you have actual bubbling and gas production going on. A, aroma change. Aroma is just a fancy word for smell. You experience a smell change. Something tastes or smells like lemons, and now all of a sudden it smells like pizza. That's a chemical change. Shoot. Oh, I remember. Color change. Anytime you're performing a chemical reaction and you experience color changing, so something goes from blue to green or no color to red, that could be an example of a color change. Now, be very careful because something like Kool-Aid mixing with water is not a chemical reaction. We are experiencing a color change, but that's because the powder you are putting into that water itself is colored. So that would technically not count. T, a temperature change. So if you're doing a chemical reaction, all of a sudden you have a thermometer involved and you see actual the thermometer is increasing or decreasing in temperature. And sometimes you can even feel that occurring in some reactions. So a temperature change could be an example. And then the last one, a solid formation. So sometimes when you do a chemical reaction, you can combine two liquids and you actually form a solid in that reaction. And we call that solid a precipitate. Now that's a big fancy word. I don't need you to remember that. It's just something to think about. You can combine two liquids and you can make a solid, which is an excellent example of a chemical change. So hopefully that you can use that acronym at some point throughout this unit as an example of, did a chemical change occur or did a chemical change not occur? Just to be aware of. I'll erase this just before I move on to my next slide. Oops, touch audio cable. All right. All chemical reactions can be broken down into two things, either reactants or products. Reactants are simply what goes into a chemical reaction, what you start with, your beginning ingredients, and your products are the chemicals that come out of it. So if we think about baking a cake or if we're baking anything, our common reactants might be flour, sugar, eggs, maybe some vanilla, all of these different things mixed together. And then we go ahead and we put it in the oven for a while. We put it in there for 10, 20, 30 minutes. Excuse me. And we pull those ingredients out of the oven. We don't have flour, eggs, milk, sugar, all of those things. We don't have it anymore. They are permanently changed. You have a full-on cake at that point. And no matter what you do, you are not going to be able to separate that cake back out into flour, sugar, and those ingredients we already talked about. So when a chemical reaction is going on, we're losing reactants typically, and we are gaining our products. Now, there are some types of chemical reactions. There's a long list of things, of different types of chemical reactions, but I'm going to keep it simple. Two that are the most basic types. You have combustion reactions, and you have synthesis reactions. A combustion reaction is simply when anything is being burned or any time that fire is produced, that burning is what actually causes a chemical reaction. And in that, you're producing CO2. That's how our internal combustion engines work. That's how campfires work. Candles, lighters, anything that uses fire produces CO2. And that's kind of where our greenhouse gas effect or greenhouse effect is coming from, where all this production of CO2 just because of our combustion reactions going on inside of our motor vehicles and inside factories. The other type is synthesis reaction, where you actually have two or more substances being chemically combined to form a new one. So some of the reactions that we're going to deal with will be a synthesis reaction where we're not producing two new things or two new products. We're just taking two reactants and we're making one new product. Now, here's an example of how we write or commonly write chemical reactions in science. You have a reactant 1 plus a reactant 2, and you have a forward arrow saying that you are producing or you are moving towards product 1 and product 2. So some examples of chemical reactions that you could see is we have the first one, we have C, so that stands for carbon, plus O2, that's oxygen, and it is producing CO2 or carbon dioxide. And we're going to go through later on in this unit how to actually write those symbols and those names for these elements, just very basic stuff. And then we have another example of hydrogen gas or H2 or hydrogen gas plus oxygen gas or O2 yielding 2 H2O molecules. So those are two common examples of chemical reactions. Now, they may not mean much to you right now, but we're going to get into what those reactions mean and how to write them here in a moment. So just before we do break it down, I want to make sure that you understand the symbols we are including in those chemical reactions. So we got a plus symbol. That just means separates two or more reactants or products, meaning that you are adding either reactants or products together. You have a yield sign or a forward arrow. That's just saying you are producing products or you're moving towards products. You start with reactants, you're moving towards those products. You have another yields arrow, which are forward and backward. And that's just saying that you are balanced. You are producing products, but you are also moving from those products back to reactants. So sometimes the reactions can go backwards and forwards. The next four are just pretty simple. You've got an S in parentheses. That just stands for a solid state of matter. You have an L in parentheses. That's a liquid state. G, a gas state of matter. And then this is a new one, an aqueous state of matter, just meaning it's some sort of solid dissolved in water. We won't deal with aqueous solutions very much. Most of our stuff will either be solid, liquid, or gas state. We'll be combining those when we do some reactions. Now, a skeletal equation is just simply the basic chemical formula written out. So here we have aluminum solid plus Br, which stands for bromine or bromide in this case, bromide gas. And it's chemically combining. So those two reactants, aluminum and bromine, are being combined and yielding aluminum bromide, which is a solid. So what would a skeletal equation be for carbon reacting with sulfur? I would like you to pause this video here, and in a moment we'll go through this, but this will be something that I want you to put in your notes just as an attempt. So based on the example I have right there on the board, what would you say carbon combining with sulfur would look like? So go ahead and pause if you haven't. All right, so now you've unpaused. Let's just write out what this skeletal equation might look like. So this is really simple here. We've got carbon as it says right here. So I'm just going to write carbon. If we look at the periodic table, carbon is represented by the symbol C. We said we're going to add it or react it with sulfur. So I'm going to put a plus, just saying we're combining it. And then sulfur, if you go to the periodic table, actually represented by the letter S. And for simplicity, we're just going to say we have carbon solid, we have sulfur solid. If you didn't have that, that's okay. I just felt like including it. We're going to put our forward or our yields arrow, meaning we're producing products. And our product in this case, and hopefully you can see that okay, carbon sulfide, CS, and that would be a solid. If you can't see it, that's okay. I can talk you through it. But this is just a very simple equation, almost like a math problem. All right, so here we have that exact same problem. The only difference from this one and the one I just did is I have carbon solid plus sulfur solid, which end up producing carbon sulfide or CS2, which is a liquid. So here we have an example, two solids making a liquid. What is the main problem with the above skeletal formula in your opinion? Think about the law of conservation of mass. This is really important. Think about how many atoms are present on the reactant side over here and the product side over here. So go ahead, take a minute, think about it, and then we'll come back. So then you can press play again. So you paused. We have a reactants of products. We got carbon solid plus sulfur solid yielding or producing carbon sulfide liquid. What is the main problem here? And that's the fact that right now, if you didn't get that, this is okay. We haven't talked about it until this point. I just want you to see if you can figure it out. We have carbon, we have sulfide, And here we've got carbon and sulfide. But the real kicker here is this number 2. That 2 is called a subscript, and it's telling you that you have 2 sulfur atoms. So on this side, we have 2 sulfurs. Over here next to sulfur, we do not have a 2 written. So that automatically means on that left side that we only have 1 sulfur. Now, due to the law of conservation of mass, we've already said that you can't have more mass or you can't gain mass or lose mass. So if we have 2 sulfurs on our product side, then we have to have 2 sulfurs on our reactant side. So I'm just going to go ahead right now and I'm going to make 2 sulfurs. So I'm going to put a 2 out in front of our sulfur. And in a minute, we're going to get some more practice with this. And I'm going to talk through it. But that was just kind of the beginning portion of that. So let's continue on. And I didn't erase everything. Now everything's gone. All right. So chemical equations must show that matter is conserved during a chemical reaction. Like I just showed you, if you have 1 sulfur on your product side, then you better have 1 sulfur on your reactant side. But if you have 2, or if you have, and it works the other way around, if you have 2 reactant or 2 carbons, then you better have 2 carbons on your product side. You can't destroy matter. We can't create it. We can only change what we already have. So the mass of the reactants equals the mass of the products. This isn't new. We've talked about this in different ways already. So we refer to this in chemistry as balanced or a balanced equation. So how we balance these is we use what we call coefficients, large numbers or multipliers that go out in front of our symbol. And we use subscripts, which go below, and they're small numbers, of our elements individually. So if we look at our coefficients up here, I have 2 CO, 3 CO, and 4 CO. What that's saying is, just like in math, if I put a 2 out in front of parentheses, that's telling me I have 2 carbons and 2 oxygens. Or if I have a 3 coefficient, that's saying that I have 3 carbons and 3 oxygens. Versus a subscript, which is that little number down here. It could be a 2, it could be a 3, it could be a 4, it could be 9. It doesn't matter. Excuse me, depending on the compound. But this is saying that I have 2 hydrogens or 2 oxygens or 2 chlorines for whatever I'm chemically combining with. I use a coefficient if I need to add more molecules or more compounds. I use a subscript if I just need to change how many of an element I have in a compound to balance it out. We're not going to get super deep into this balancing of coefficients and subscripts and chemical reactions, but I just want you to know the very basics of it. So we're going to get into that in one moment. So what can I do to balance this equation? We just talked about coefficients and subscripts. So let's take a look at this first one here. Here we have CS, carbon, solid. We have SS, and we've already talked about this one. So this one's pretty quick here. Like we said before, we've got 2 sulfurs. I need to have 2 sulfurs on this side. So here we've got a 2 subscript. And then because I have 2 sulfurs on the product side, I need to have 2 on the reactant side. So I add a 2 coefficient out in front. What I wouldn't want to do is change my equation to S little 2, because that's changing my compound. That's changing my element completely. And I don't want to do that. I just want to add how many sulfur solids I have. So I just want to put a coefficient out in front instead. Now here below, we have an equation we've seen already in earlier slides, but we haven't balanced it yet. We have aluminum solid plus bromine 2 liquid combining and producing, keyword producing, aluminum bromide Br3. So this one's a little bit more difficult. It's not as simple as adding a 2 coefficient. And the reason why is if we look on our reactant side, and I'll write these up here again just to help you out, reactants and products. We have a 3 and a 2 or 3 on the product side and 2 on the reactant side, that's hard to balance. So we got to think about a multiplier of 2 and 3 that go into each other. So I'm going to simply write down underneath our elements that we have involved in our chemical equation. On the product side and the reactant side, aluminum, we don't have anything written as a coefficient or a subscript, so I only have 1 aluminum atom. Now, if I look at my reactant side and look at bromine, I have 2 bromines, Br2, so I'm going to put 2 on this side. Now, our final product, we have aluminum bromide. So this is a good example of a synthesis reaction, combining 2 things and making 1 new one. Aluminum, we still only have 1. There's no coefficient. There's no subscript, so we have a 1 there. So our aluminums are balanced. Br, or bromine, we've got 3. So how are we going to balance that? Like I said, we got to find a multiplier that goes into both of them. So if I take 2 and a multiplier that goes into 2 and 3, the first one we come across is 6. I am going to take 2, I'm going to multiply by 3, which is going to be equal to 6. So I'm going to add a 3 coefficient up there, making 6 total bromines on my reactant side. Now on my product side, I have, like we said, we have 3. I need to turn 3 into 6. So I can't change my coefficient to 6. That's not possible. That would change my whole equation. So let's get rid of it and let's make a coefficient and put that on there. So if I take 2, 2 times 3 is equal to 6. So this would be my balanced equation. We have the same number of aluminums on the reactant side and the product side. We have the same number of bromine atoms on the reactant side as we do on the product side. Only a few more slides. I know this is a lot, but sometimes we have to experience this a little bit. So we already just went through this one on the previous slide, so I'm not going to go through this one again. And if you need to see that aluminum bromine reaction, just go back in the video, backspace. Here we've got another one. We have NaS plus N2 gas producing sodium nitride. Na is sodium, so it's a different element than just N. N is just nitrogen. And this is another synthesis reaction. We're taking 2 things and combining them into 1. But let's take a balance here. So this one is extremely similar as the one we just did. We have Na, which is just 1 on the reactant side. And we have N2, or nitrogen. We have 2 of them. Remember, we got the subscript 2 here telling us we have 2. And then if we go over to the product side, we have Na again. We have 1. And then we have N. This time we have 3. So think about what we just did in the previous equation to balance this out. We're going to multiply by 2 to get to 6. So nitrogen, now we have 2 up here. Okay, Na making nitrogen 6. But now we've got a problem. We have 2 N3s, and we multiplied nitrogen by 3 or by 2, so now we have 6 total, like we have here. But now I've got a 2 out in front of Na, so that's saying that I have 2 sodiums. So now I'm unbalanced again. So I need to take Na, or I need to balance my nitrogen. So I have 2. I'm going to multiply by 3. So I'm going to move 3 out in front, making 6. So my nitrogens are balanced. And now all I need to do is take my Na, my solid, and I'm going to add a 2 in front. And now I have a balanced equation here. So that was a little bit more intense. We had to add another step, but not super difficult. It's just basic multiplication at this point. So if you're struggling with this, and that's okay, this is new and this is a big idea. If you're struggling with this balancing, just stop, let me know, and I'll give you some practice problems as well. But I'm going to give you some more here in a second. Let me just erase this and we'll continue. So we're going to do some practice with this, just like I said. So here we've got 3 more practice problems. And I'm pretty sure, yeah, this is the last slide here. I have the first 2 on your note sheet. If you want a challenge, you can try the third one just to get you thinking a little bit, but it's exactly the same as what we just did. So I am not going to practice these ones on the board right now, but if you do need some help with this, just come ask me in a second. But I'd like you to try on your own first. So go ahead and you can stop the video. Hopefully you have your notes all figured out after completing these practice problems. And then once you have, let Mr. Wells check it and we'll see if you did them right. But make sure you write out all of the elements in each of them and you count how many either via coefficient or subscripts you have to figure out that total at the beginning. So stop the video, go ahead and practice. We'll see you later.